Oh. Yeah, and Yes, it does. Yes. No, what should.
Hi, this is okay? Okay. Seems to.
Ready? Ready to go?
Yeah.
Ready to go. So I think we are 5 minutes not late. I think usual 5 minutes of delay. So this third presentation for the afternoon concerning peer-to-peer is dedicated at computing. The first one was an overall overview of what was peer-to-peer concepts, architecture, projects, challenges, etc. And the second one was peer-to-peer applied to, we'd say, research and documentation. And now, third one is on computing, not grid computing, peer-to-peer computing. Interesting difference between grid computing and peer-to-peer computing. Well, I introduce Franck Cappello. Franck Cappello is working Université of Paris 6, 11, Paris Sud, south of Paris, sorry. Also working for INRIA, and so on. Well, he will give more detail on what he is doing, for whom he is working, and what is his expertise. Franck, please.
Okay. Oh, sorry for that. So today we'll try to discuss about the problem of executing parallel applications and high-performance parallel applications or high-throughput parallel applications on peer-to-peer platforms. So I am Franck Cappello. I belong to CNRS. I also lead the cluster and grid group at Paris 11. And I also lead this INRIA Grand Large project, which is dedicating to the study of how to compute and share data on a large-scale distributed system. So what I will try to present here is something related to large scale. So most of the work that will be presented in this talk is funded by a French government initiative which is called ACI Grid. So okay, so this is the outline of the talk. So I will briefly make an introduction describing grid and peer-to-peer. And then I will discuss about two main points about computing on peer-to-peer systems. So the first point is a system issue. How do you organize a peer-to-peer platform for computing? And the second problem is how you program a peer-to-peer platform for high-performance computing. You will certainly need some kind of programming library. So I will discuss about RPC and MPI, programming on peer-to-peer systems. So what you can see here is the V. V means volatile. So this means that we have developed several message passing library for volatile nodes. And then I will, if I have time, discuss about one open issue, which is merging a grid and peer-to-peer system, and then I will finish by concluding remarks. Thanks. So this slide is quite similar to one that was presented just 2 talks ago. So in fact, I presented this slide 2 different kind of grids. So the first first kind of grid is what I can call traditional grid. So these are the well-known grids like the one that harness large sites, large computing sites, where you can find clusters or big parallel machines. And so these traditional grids usually harness a few numbers of sites. So that doesn't mean that there are few numbers of processors, of course, because in each site you can find thousands of processors. But in that case, in fact, the number of administration domain is very low. In fact, in all this grid environment, you find stable resources. So that means that, in fact, there is no crash, or you can expect that there will be no crash of one side during the execution of your application. And also, there is a strong security mechanism. So there is a very strong authentication mechanisms, and also security is enforced by some policy in each site. One thing which is very important is that if you get some result from such a grid platform, then you can trust them, because these sites belong to institutions, and so you trust the institutions that have these sites. So if we look now to large-scale distributed systems, so what we call peer-to-peer or global computing platforms, so then we can see that we have mostly PCs as node of these platforms. And so we can find a very large number of PCs, something like 100,000 nodes, for example. A very important point is that these nodes are volatile. So that means that at any time, a large number of nodes can disappear, and a large number of nodes can connect the system. And you can't predict that. Okay, so this is very difficult, a very dynamic system, much more dynamic than the grid, actually. Currently, there is no authentication mechanisms in such kind of system, so that means that security is not enforced. So you can't trust the systems. So if you are running an application, I mean a global computing application or peer-to-peer system on your PC, then you trust the person who has developed this application. But in fact, you have no protection on your PC in order to protect it from malicious applications or malicious users. So you really trust the system when you are executing SETI at home or an Upstair on your machine. One thing which is also important is that if you are using a global computing system or a peer-to-peer system for computing, then you can't trust the result that you will get from this system, simply because you will have a large number of processors. Among this large number of processors, maybe one or two users will send you some results that are corrupted. Okay, and you have to distinguish between wrong and good results. So this suggests the need for some techniques which is known as result certifications. So this means redundant execution and probability and statistics. Okay. So of course, this is the well-known large-scale distributed computing example. So this is SETI at home. It gathers millions of PC. It uses cycle stealing as a computation paradigm. And what is very important is that you can gather a lot of PC and reach a very high throughput, so something like 33 teraflops. So currently this is still a very high performance compared to the Earth simulator, for example. It's very close. But of course, you can't execute the same kind of application on both platforms. So in France, we have had something which was called decryption, and this is the same principle, but for protein sequence comparison. So this project has been turned off currently, but it will be renewed on the next year. So one of the very first applications of this large-scale distributed computing was breaking encryption keys. So if you remember, for example, there was some project in late 90s about that. So now if I consider peer-to-peer system and also peer-to-peer system for file sharing, so the best known application was Upstair, of course. And what is very important in Upstair is that after you have getting the location of a server, if you are a client, then you have a direct connection between the client and the server. So this is something very important. The other important thing is that so you store files, and if you count the number of files that are stored or the storage capability, so you have something which is in the order of thousands of terabytes. So this means that this is a very, very interesting storage architecture. And also, if you are trying to share data, so you exchange some files between all these nodes. And if you look to the bandwidth which is used, the aggregate bandwidth which is used in these systems, this is something which is close to hundreds of gigabytes or even terabytes per second. So this is something really interesting, is how this kind of infrastructure can use the network and can use the storage of the PC that are connected to these systems. Okay, another very important thing in that kind of system is that every member of the system can play two roles, so the role of the client and the role of the server. So this is something important. Okay. So if I try to go deeper in the explanation of this system, so I consider first the distributed computing platforms. So you have essentially a centralized coordinator, and you have a set of volunteer PCs. So this is using the master worker paradigm and with the cycle stealing paradigm. So this means that, in fact, all this volunteer PC will try to connect the coordinator to get the application first, and then to get the parameter for executing this application. So this is basically distributed computing. One thing which is also important is that you are using the pool model of task distribution. So that means that this coordinator is not pushing the task on the node like traditional batch system. In this system, things are going in the other side. So in fact, this is the pool model. So this worker is asking when it is available a job for the coordinator. So this thing is also interesting. So, of course, we know a lot of dedicated applications using this scheme, so SETI at home, decryption. There are lots of genomic applications like Folio at home, Genome at home, etc. And also there are some research platforms and commercial platforms. So maybe you know Entropia, United Device, Parabon, and also Data Synapse. All these commercial platforms are intended to provide such kind of computing paradigm for the industry. Okay, now if I look to peer-to-peer system, as I said, a very important thing is that every member of the system can play the role of the client and the server. And also they may communicate directly. Okay. Another feature that could be used for such kind of system is that they may be self-organizing. But I don't know if this is really something important of this in this system, or just a feature that can be used for peer-to-peer system. So actually, I don't know really if somebody knows what is the definition, the pure definition of peer-to-peer system. So it's very difficult to have a definition currently. Okay, so there are different applications that you can execute on such kind of system, having direct connection between volunteers and playing different roles. So you can have instant messaging, managing and sharing information, collaborative work, distributed storage, like, for example, Ocean Store. So there are some some projects like Globe, for example, and CX that are trying to investigate the issue of such kind of systems. And also there are some platforms that you can use to develop such kind of systems. So for example, COSM is a very well-known platform for designing peer-to-peer computing systems. Okay, now what is the subject of this presentation is in fact how you merge the two. So global computing platform and peer-to-peer system. So this is essentially a very simple scheme, but you will see that this raises a lot of very difficult issues, in fact. So the idea is simply that, in fact, you try to use distributed computing for a lot of users. Okay, so you will have several users that will play the role of clients, and they will submit jobs to a peer-to-peer system, so they belong to these peer-to-peer systems also. And in this system, you have some servers that will accept jobs and provide results for these clients. Okay, so this is somewhat a multi-client distributed computing platforms. So if you do that, you can see that this is a very simple scheme. But if you do that, you have a lot of problems that arise. So you have a problem of scheduling, security, message spacing between the server node, for example, data storage. You have also fairness problem. So all these problems are very usual in distributed systems. Okay, we know some results that can be used to solve these systems, these problems. But the main issue here is that all all these problems are renewed because of the large scale feature of the system. So here you have to deal with 100,000 nodes or millions nodes. So that means that probably you will design. You will need to design new algorithm that can scale up to this number of nodes. And this is not what you can get if you look to the history of distributed computing. All these algorithm has not been designed with such scalability in mind. Okay, so for example, you cannot have consensus on such kind of systems. You cannot use easily atomic broadcast on such kind of systems. So you probably need self-stabilization algorithm, and it's not clear today if we can really use self-stabilization algorithms in these systems. So here is one slide of Jan Foster. I have changed a little bit the title. So the original title is 3 Obstacles to Making Grid Computing Routine. So this is a change of the title to 3 Obstacles to Making Peer-to-Peer Distributed Computing Routine. So I will focus on these 2 issues. So the first one is being able to program these platforms. So you have seen this very simple scheme. Now, how can I program such kind of system? The second issue is a system issue. How do I construct such kind of system? Okay. Mm-hmm. So these are programming problem and a system problem. Okay. So now I will discuss about these two things. So first the system issue and then the programming issue. Okay. So these are the basic elements of peer-to-peer systems. So I consider peer-to-peer system as a collection of basic mechanisms and not as cultural things or I don't know. So if you consider just this peer-to-peer system as a collection of mechanisms, then you can use them and remove some part of the components, re-implement one component in the centralized way if it's better for the performance, for example, and it doesn't matter really. So the first thing you have to do is first to connect the system. So of course you will need to have a gateway to have an access to this system. So this will allow you to choose a community and to contact a member of this community to be able to integrate this community. So this is the first thing you have to do. The second thing is you will need a set of protocol for enabling communication between the peer in these peer-to-peer systems. So usually a lot of peers in such kind of system are protected by firewalls. So if you have two nodes protected by firewalls, then you have to use techniques like relaying in order to be able to have some communication between these nodes. Okay, so for example, Gigster is providing you such kind of infrastructure for enabling communication between the nodes. So you have to deal with NATs, firewalls, proxy, etc. Okay. So the third system that you will need is a way to publish resources provided by a server. So if you want to play the role of a server, then you will need to publish the resources that you want to provide for the community. So this means what kind of resources you are going to share, what role you could play in the system. Is it just providing files, or is it participating to the localization of the other resources? So what kind of protocol should be used to discuss with you? So all these things should be published in order to allow the other nodes to discuss with you. So this is the third basic element. The fourth basic element is, of course, a resource discovery engine. So it is intended to establish a connection between a client and the server that will provide the resources that the client is looking for. So this resource discovery engine is something which is deeply studied currently. So we have, in fact, 3 generations of this resource discovery engine. So the first generation, of course, is using the central, So the central index, so this is Upstair. So this is something that has been explained in one of the previous talks. The second generation is using flooding. So, for example, Glutella is a good example of this second generation peer-to-peer resource discovery systems. And the third generation is distributed hash table. So, for example, CAN, CORD, pass-through, all these things are just providing you a way to find resources in the peer-to-peer systems. But they are not providing all the other mechanisms that are used and that are required for building a peer-to-peer systems. Okay. So if you have these four basic elements, you will need a fifth one, which is a coordination scheme. So if you really want to compute on such kind of system, you will probably need a coordinator. So this coordinator can be centralized or it can be distributed. But anyway, you will need a coordinator. Why? Just, for example, if you want to submit tasks on the system, distributed task, you will need something which will distribute the task for you, detect faults, for example, so the volatility of one node or several nodes, and relaunch the tasks that have been launched on failed nodes. So all these things is done using coordination systems. And this is really something central in the case of computing on peer-to-peer system. Okay, so probably you may be able to execute this coordinator inside the client itself. But maybe it's not a good idea, and it could be preferable to use this coordinator as a service. So one node may play the role of the coordinator for you. So you may try first to look for such kind of coordinator node and then submit to him the task that you want to be executed on the system. So now I will just detail two systems, so XtremWeb and BOINC. So XtremWeb is developed at LRI in our team and BOINC at UC Berkeley. So this is, in fact, the second generation of SETI Atom. So here is XtremWeb. So XtremWeb implements a subset of the 5 mechanisms that I have described up to now. So there are 3 entities. So the client, which will submit jobs, the coordinator, which will coordinate the job submission and the job execution on the worker, and the worker, which actually will execute the task. So this is a kind of peer-to-peer system because all the nodes here can play the role of the client or the worker. And in the next generation, several nodes in the system will also play the role of the coordinator, so because we will have a distributed coordinator. So if we look to this organization there, what you see is simply the same as the one used for SETI Atom, for example. You have a coordinator, which is also the client, and it submits tasks to the worker here. And this worker just gates the application and gets the parameters and returns the results for the execution. Here you have a huge database for storing the parameters and the results. Okay. So now if you want to use peer-to-peer scheme, then any of these workers or all of these workers can play the role of clients and submit tasks to the system. So if they want to submit tasks, they have to submit it to the coordinator. And then the coordinator will simply forward the task to a worker which is actually willing to execute applications. Okay, so what you have here is simply a scheme for sharing worker resources by multiple clients. So this coordinator is currently centralized, but of course you can imagine to distribute it and to distribute it among the nodes themselves. Okay, so this is a kind of Phi Optical Design if you want to harness different XtremWeb platforms. So this is something which is actually running in France, and I will detail that later. Okay. So if I look to the worker architecture, so this worker is simply a daemon which is running on your PC, and it can execute binary application. So it will download an application that can be a binary, or that can be a Java application. So it runs on Linux, Sun OS, and also Mac OS X and Windows. So this worker is using a mechanism to bypass firewalls. So here you have a firewall, and here you have the coordinator. So what we use is simply using an RPC scheme. So if this worker is submitting an RPC toward this coordinator, then usually the firewalls are configured in a way that they will allow the comeback of the results of this RPC. Okay, so this is something which is used in most of the global computing platforms, like SETI Atom, for example. Okay, so in this system also we use SSL tunneling in order to have a strong encryption of all the application, the parameters, and the results that are transmitted between the worker and the coordinator. So here is the client architecture. So the client is in the form of an API. So this is something you can link in with a Java program. And within this Java program, or also in the C program, you can simply use this API to submit tasks to the system. So the client will simply contact the coordinator submitting tasks, collecting results, and also for monitoring the coordinator. So monitoring the coordinator means that you can discard some tasks or discard some results, and also you can choose the worker that will be used for the execution. So, so typically the kind of application that you will execute on this platform is our multi-parameter application, bag of tasks, master worker, and basically embarrassingly parallel applications. Okay. So I will not go into detail about the security model used in XtremWeb, but one thing is very important. This is the sandboxing. So sandboxing means that you will try to protect the worker from malicious applications and from also malicious users that will try to corrupt this machine. So in order to do that, you will need to run the application inside what is so-called a sandbox, which will trap all system calls and check if all system calls are correct according to a security policy. Okay, so this is something very important. And you will see such kind of sandboxing more and more in peer-to-peer and global computing systems. Okay, so I skipped the rest. So this is the coordinator architecture. So this coordinator is managing a set of databases. So there is an application database where all the applications are stored, a task database which stores all the tasks that have been submitted to the system, a result database, and also some statistics. So here you have a scheduler which is simply detecting the volatility of the nodes and which simply relaunch a faulty execution on another available node. So here you have a task selector which simply selects the task from the application database and the task database and in fact give this information to the scheduler for launching the application on the execution on the node. Mm-hmm. So this is one of the first applications of XtremWeb. So this is the Peerage Observatory. And the goal of this observatory is to understand the origin of very high energy cosmic ray. And this, for this, physicists are running a simulator which is called HERES for Air Shower Extended Simulator. Yes. And so this is a kind of Monte Carlo simulations, and each simulation takes about 5 to 10 hours on a PC. So this is the configuration which is used with XtremWeb. There is a database in Lyon storing all the parameters on the application for this Peerage Observatory. Then there is a server at LRI, which is the coordinator, in fact. And then you have several PCs there that are working for this application. So the estimated number of PC that will be used for this application is about 5,000. So this is a very classical scheme of distributed computing. This is similar to SETI Atom, in fact. So we have deployed this system in order to test the performance of the system. So we have used several clusters, in fact, around the world. So there is one cluster in Madison, Wisconsin, which is running under Condor. There's one cluster at Grenoble running under PBS, which these are two batch schedulers. And there is also one cluster at LRI, which is my lab, so working under Condor. So here is the configuration. There is one XtremWeb client at LRI, one coordinator, and so all this cluster will run the worker of XtremWeb. Okay, so what you see here are firewalls. So because all these clusters are simply, and all the nodes of this cluster are simply requesting tasks using RPC call to this coordinator, they can cross their firewall and they can get back their parameters, for example, or they can submit their result to the coordinator without changing anything in the configuration of the firewalls of all the systems, except for the coordinator here, which should be open for the XtremWeb connections. So here is an execution of this application. So W means Wisconsin, L means LRI, and G means Grenoble. and here is the number of processors used for the executions. So this is the time, the execution time in minutes of the full applications, and this is the number of processors used instantaneously. So every minute we show the number of processors that are used for these computations. So what you see here is that we have up to 451 processors at this step, and for the other configuration you have a lower number of processors. So this is the actual execution time of the full application, something like 55 minutes. And you can see that if we use a lower number of processors, then of course the execution time is increasing largely. So a very important thing is how this system can survive massive faults. So you can have, as I said, a lot of nodes that simply disappear of the system or connect the system. So how this system can resist to these events. So what you can see is exactly the same diagram with the execution time in minutes here and the number of processors used. So we have started the execution here and using up to 350 something processors. And then at this step, we have lost the connection with Grenobles. So this means that all the processors that were used in Grenoble have simply disappeared of the systems. So this is why we have this very sharp reduction of the number of processors. And then the system continues execution for a few minutes, and the connection is reestablished with Grenoble. So this is what we see here, and then the workers that are running at Grenoble simply tries to reconnect the dispatcher at LRI for getting some tasks to execute. So this is what we see here, and we reach this plateau, which is another plateau of fault-free execution a few minutes after the big crash of the Grenoble connections. So this is simply showing that this system can resist massive faults of workers. Okay, so this is an application which is used in industry. So this is a ray tracing application where it's quite simple to reprogram a ray tracing application for XtremWeb. This is a comparison between XtremWeb and MPI, and there is no doubt here that it is quite easy to have the same performance between the two systems because there is no communication between the different nodes that are executing these applications. So this is a number asynchronously parallel application, so that's why we have the same performance as MPI. Okay. So there are a lot of projects using XtremWeb. I have no time to go into detail there. Okay. So now this is the Berkeley Open Infrastructure for Network Computing. So this is the next generation of SETI Atom. This is developed by David Anderson, who is the leader of SETI Atom, and at UC Berkeley. So, okay. So the goal of BOINC is to harness the resources of the UC Berkeley, so the University of Berkeley, and to provide these resources, I mean the PC simply, of the different labs to different projects. So these projects are running different applications, and there will be a set of applications, and all these applications will share the same resources. So this is quite similar to what we are trying to do with XtremWeb. So there are multiple autonomous projects. The participant can select the project to which they want to participate. This is supporting a data-intensive application. I will show why. And this is also using redundant computing. So redundant computing is used here mostly for the problem of result certification, because you can't trust the results even if they are provided by PC that belongs to UC Berkeley. You need to have some replication strategy. So here is a view of this project. So you have a database which stores the application, the parameters, and the result. This is very similar to XtremWeb. You have something which is the project work manager, which submits tasks to this database, and then you have a scheduler which schedules the task from the database to the workers, which here are called core agent of BOINC. The main difference between the two systems is here. So here you have a data server which is different from the application server. So they are decoupled. And in this data server, the core agent can get the parameter and send the result. So this is something which is a little bit different compared to XtremWeb, but this is really easy to redo this design using XtremWeb. Okay, so here are the application of BOINC. So, for example, you have SETI atom, of course, astropulse, folding atom, maybe, and climate prediction, maybe. So the status is that currently it is funded by NSF, and it is in beta test. So what are the user feedback for this platform? So now we have installed a series of this platform, and we have some feedback. So first of all, the main problem is the human factor. So the system administrator is always seeing this kind of system as a security hole for the platform, for the PC that he is managing. So this is very difficult to convince a system administrator to simply install the application, the XtremWeb application, on one PC. So the second problem is that installation is very difficult because the network are all different. So you have a very distributed network, that are sparse and that use a lot of proxies or firewalls. So you need to have an installation which is different for every site, in fact. The use of network resources also is a big problem because people are using the network for something else. So now they have to share the network with you because you are doing execution, parallel execution on their PCs. And if this thing slows down their use of the network, then they are not happy and they want to discard simply your project. Also, you have to deal with the complex topology, so I have discussed already with that. Another problem is that you are dealing with resources that have limited memory capacities, limited network performance, so that means that the application domain is quite restricted for this kind of platforms. But the basic need, what is really need for this system is a way for programming parallel application which is transparent for the users. So user can simply use RPC or MPI programming models, but they don't want to deal exactly with the problem of volatility of these kind of platforms. Okay. So I will just present one thing, which is RPCV, and then I will go to the conclusion. Okay. So if you try to develop a fault-tolerant message passing library, then you have to face with a lot of previous work. Okay, so this is something which is not new. There is a lot of previous work, and this is a classification that you can find in a paper that we have passed last year in supercomputing about MPHV. So if you are interested, you can look to this paper, and you will see these classifications of fault-tolerant message passing libraries according to the level in the software stack where the fault tolerance is managed, and also the technique which is used for fault tolerance. So if we look to the two software that we have designed along with XtremWeb, so these two message passing library, they sit at the lowest possible level. So this is something which is lying really at the lowest possible level of the software stack, and this is using so-called pessimistic message logging protocol. So what is the goal of RPCV? So V is for volatile nodes. So the goal is to execute RPC-like applications on volatile nodes. So the programmer view should keep unchanged. So that means that the programmer will use simply a RPC call with the function to call and the parameters that should be passed to these functions. And the server itself will run the functions, will execute the functions with the parameters. The problem we have is that we have to deal with volatile nodes, with firewalls, and we won't be able to execute recursions. So this is interesting, for example, for application of combinatorial optimizations. So the objective of this RPCV is that we want to provide an automatic fault tolerance mechanism which is transparent for the programmer, which can tolerate client and server faults. So that means that even the client can disappear in this system. It should be able to pass firewall and avoid global synchronization. Another very important point is that if you are designing such kind of algorithm, then you have to prove it theoretically. Because if you don't do that, then you will face a lot of tricky bugs. So this is the design of this RPCV platform. So you have here simply XtremWeb, which is working as a transport layer for these RPC systems. So the client is simply using the RPC API, so for example, XML RPC or something else, and then its requests are simply forwarded to the client, the XtremWeb clients. So this is a translation between a function calls to a task executions. So inside this box, this is task execution, and at this level, this is function calls and function reply. Okay, so this is the abstract level, and this is the implementation level. So when the client has the task, then it sends to the coordinator. The coordinator selects a worker for the execution, and the worker simply launch the executable that run the functions and pass the parameter to these functions. And when it gets the result, the system is also used for transporting the result back to the client. So here you have the fault tolerance layer. So we use, for the client, some message logging techniques plus some message counting techniques. We use passive replication at the coordinator side, and also we use message logging at the worker side. So if we look to what happened dynamically, so you retrieve the same scheme as the previous one. So the client can submit task to the coordinator, and then a worker can get a task from the coordinator. So now if you suppose that this worker dies, then it can roll back directly on the same machine if the machine is simply coming back, okay? Or, and if the machine comes back, then it can put the result back to the coordinator. But if the machine doesn't come back, then a new worker will be selected by the coordinator, and this worker will synchronize with the coordinator to see what kind of task should be executed. And then this worker will send back the result. The client can disappear itself. So in that case, it can roll back on the same machine and re-execute and get the result back from the coordinator. But if you can't restart it from the same machine, then you can restart the client in another machine. So this is for mobile clients, in fact. So you can implement mobile clients for this using this scheme. So in that case, the client can synchronize with the coordinator for getting the task that have already been sent to the coordinator and getting the result. But the coordinator itself can disappear. So in that case, we rely on a replication scheme, which is a passive replication scheme for surviving this problem. So in that case, if the client cannot connect to the coordinator, the first one, then it will use the second coordinator, and the worker will do the same. If he cannot connect the first coordinator, then it will use the second one. So what you have seen here is that we can go from one complete system to another one if there are a lot of failure in the system. Okay. So these are the performance of this system. So this is an execution with faults, without faults. So in fact, what you see here is that the system scales. So if you use more processor, then you can have a speed up for your application. And here you have the execution time when you have some faults that occur during the system. So this is one transient fault every second on the system, and this is without faults. So what is the conclusion of this slide is that if you are implementing such kind of system, then in fact you can survive quite easily the node volatility of the system. So I will go to the conclusion, I think, because I have no time. So this is for MPI. This is also working. This is also surviving massive faults and very frequent faults. And so I will go to the conclusion. So the previous slide was about executing grid services on top of this desktop grid on this peer-to-peer system. Okay, so this is quite similar to this RPCV scheme, but instead of just executing a PC, in fact, we are executing grid services. So as you have seen, in fact, high-performance computing on peer-to-peer system is a long effort. There are still many issues to be solved. So the global architecture itself is not completely fixed. The user interface and the control languages are not defined yet. Security is a major concern. Large-scale storage has not been considered in this design. You have seen some results about message passing libraries with RPCV and MPGV. And there is also a major issue concerning large-scale scheduling. So this is something which is pretty new, in fact, considering 100,000 tasks on 100,000 nodes for multi-client, multi-application. It's something which is quite tricky and difficult to investigate. And of course, we need the validation on real applications. Okay, that's all. So if you want to have more information, you can just see this bibliography.
Okay, thank you very much, Franck.
Thank you.
Well, I think we have a few minutes while we are preparing for the next presentation, few minutes to ask a question to Franck. Or anyway, if you don't have a question now, you can contact Franck. You have identified him. Okay, question? Question from the floor? No. Well, I'm trying to ask you a question. There are lots of pieces of technology in all what you have explained here. You have been focusing much on security problems, but security problems seen from firewalls, I mean firewalls blocking or who could block the system, but not security seen from the user side. I mean by this, how does the different users authenticate and transmit their authorization?
Yeah,
so the question is related to all the discussion we have in other session about authentication architecture and exchanging authorization.
Sure. So this is a very difficult issue, in fact. So the problem is you need to design something which is scalable. So of course you will not manage a list of 100,000 logging on every machine. So you will probably need a system of community. So, but this is not yet completely clear. So I think this is still to be investigated, and this is really difficult because. Also, you have the problem of consistency of this right, of this access right. So, who will store these things? If you want to do something which is scalable, you will need probably to have some replication schemes. So, if you have some replication of this database of access, right, then maybe you will have to survive some faults and some corruptions. And this is not really easy to manage, I think.
Okay, thank you. So hopefully a lot of work to do.
Yeah, sure.
Okay, so this will motivate and explain your job. Thank you again, Franck. And as we are